So continuing our discussion with packing fraction. So as I said, the packing fraction is volume occupied by atoms in the unit cell divided by volume of the cell. Can you tell me what is volume of the total cell? Since length, breadth and height of a cubic cell, we have considered first a cubic cell. So the length, breadth and height of a cubic cell is A, so the volume is A cube. It's very logical. Okay. Now comes volume of atoms. Now can you tell me what is the contribution of the 8 atoms? We saw that the contribution of the 8 atoms was equivalent to 1 atom, and we need to calculate the volume of this 1 atom. We know that the atoms are considered as sphere, so we can just write the volume of a sphere, 4 by 3 pi r cube. Now what is atomic radius? As we discussed earlier, these atoms are not small, but these atoms are actually big, and we calculated the atomic radius by half the distance, and remember the atomic radius in case of simple cubic was found to be a by 2. So what will be this value? So it will be 4 by 3 pi, and what was r? R was a by 2 whole cube. Okay, so this value we put it here. Okay, so which is 4 by 3 pi, so we get a cube divided by 8, because 2 to the power 3 is 8. So what is the answer? If you calculate it, you will get pi by 6. So this pi by 6 is nothing but 0.52. So packing fraction is just a ratio, and the value of packing fraction gives you an idea how much this is packed. You see, this is really packed. See, these atoms are bigger. As I said, these atoms are not small, these atoms are big enough. Okay, so let me draw this one in a better way. So consider the front side. Okay, so say this is the front side of a cubic lattice. So these atoms, they actually are like this. So let me draw the complete diagram, only then you'll get an idea. Okay, so the first atom is this much big, the atom here is this big, the atom here is this big, and the atom here is this big. So this is the front view. You know, there are also atoms in the other corners, so I'm not drawing that. I've just drawn the front view, and you can easily see from this diagram that in case of simple cube, if you take two neighboring atoms at the two corners, so this is a neighboring, so this is the distance between the neighboring atom center. If you make it half, the distance was a, and if you did it half, a by 2, you are actually getting the atomic radius. So this is nothing but the atomic radius. This is the actual diagram. The atoms are actually very much big, and the amount of space available, these are the vacant space available, it's not that much, it's very less. So packing fraction gives you an idea of how much vacant space is available. So can you guess, if I take a face centered lattice, will the packing fraction be more or less? I mean, will the a volume acquired by the atoms will be more or less? It will be more. So if I can draw the front view of a face centered, okay, let me draw the front view of a face centered. So this is a cube. The cube has its other backward side, but we are actually looking at the front view. So what happens in the front view is, you have this, and this is the face centered atom, and these are the atoms at the corner. So these are packed, it's not empty. So in the diagrams, when you are seeing a cube having atoms here, here, here. This is a fake diagram. This is not that much true. It doesn't reveal the entire information. This is a true diagram. The atoms are actually big, and you see in the face centered, the atomic radius is half the distance between this point and this point. You can easily see. So if you take this point and this point, then half will give you the atomic radius. Okay, so for this also, this point and this point, then the half will give you the atomic radius. So hence in face centered, we actually used this atom and this atom to calculate the atomic radius. Now can you calculate the packing fraction in face center? It's very easy. The lower part will be a cube as it is. There will be no change because face center is itself a cubic center. And do you remember what was the contribution of all the atoms? We know that the corners have 8 atoms and the faces have 6 atoms. But since these 8 atoms are not truly the 8 atoms of the cube, this was equivalent to 1 atom. So having these 8 atoms was equivalent to 1 atom because each of the 8 atoms was shared by 8 cubes, and having 6 face centered atoms was equivalent to only 3 atoms because each of the face centered was shared by 2 cubes, as we have discussed earlier. So what is the actual number of atoms per cell of a face centered cell? It is 4. So to find the volume occupied by atoms, so what are the number of atoms? It is 4, and you have to multiply with volume of each atom, that is 4 by 3 pi radius. Do you remember what is the radius of face centered cell? The radius was a by 2 root 2. If you go back to the lecture, you can find this is discussed earlier. So that was a by 2 root 2. Agreed. So this value, if you calculate, you will get for the face centered as pi by 3 root 2. So it's pi by 3 root 2, and this was actually 0.74. Yes, as we guessed, we got the answer. We actually guessed that the amount of volume that will be occupied by the atoms will be more, hence the value of packing fraction is more. Why the value of packing fraction is more than the value of packing fraction in simple cubic? Because for packing fraction, this particular value is more. This particular value is more because the volume occupied by number of atoms in the cell was more. How about body centered? Yes, let us calculate. So this is so body centered. Let us look at the front view. So body centered is this, and the cube has a atom here and other big atoms are here. Okay, I'm drawing a rough diagram. So let us calculate. So what was the total contribution of atoms? The total contribution was 2 multiplied by 4 by 3, okay, pi. So remember what was the atomic radius in case of body centered? The atomic radius was root 3a by 4. So if you remember from the last lecture, it was root 3a by 4. Okay, so if you put it, so this is the volume occupied by atoms in the unit cell divided by a cube. Okay, so you will get a value of, so it's very easy to evaluate, root 3 pi by 8. Okay, you will get root 3 pi by 8. And can you just give a guess whether the packing fraction will be more or less? It will be between simple cubic and face centered cubic lattice. It's very logical because in the face centered we have more number of atoms, so they take a larger space, and in cubic lattice we have less number of atoms, only 8 atoms, and in body centered we have 8 plus 1 9 atoms. So more number of atoms are in the face centered, and hence the packing fraction of face centered is more. Now once we have completed our discussion on packing fraction. Now we will move on to discuss Miller indices. So Miller indices. Now before discussing the physical meaning of Miller indices and what was the reason that actually gave birth to Miller indices, we will just evaluate how Miller indices are calculated, and this will be just a mathematical lecture. So the entire physical meaning of Miller indices and why we had to find Miller indices will be found once we talk about the reciprocal lattice, we talk about the diffraction in crystals. After that, the invention or of the Miller indices or the requirement of Miller indices will be clear. So this lecture will just give you a mathematical viewpoint of Miller indices. So let us see. So what are the steps for Miller indices? Okay, so here are the things that you need to do to calculate the Miller indices. The steps I have mentioned here. Okay, so find what are the intercept at which the plane is coinciding with the axis, and then take the reciprocal of these values. So Miller indices is actually indices or the number given to a plane. They are like the fingerprint of the plane. So every plane has its own Miller indices. Okay, so Miller indices actually differentiates different types of planes. So let us calculate Miller indices in these three cases, for these three cases, and then we can move on understanding some complicated cases. Okay, so what was the technique behind Miller indices? The technique says that find the intercept. Okay, what do you mean by intercept? So let us assume as a coordinate system. You see the three axes. Okay, so let us consider this as x, let us consider this y, and let us consider this as the z. Now this is the plane. Let me just draw lines. Can you see the plane? Okay, I'm drawing blue line on the plane. This is the plane. Can you tell me, is the plane intersecting anywhere on the x-axis? The plane is not intersecting x-axis. So I can write the point at which the plane intersects the x-axis is infinity, because it never intersects the x-axis. Can you tell me where does it intersect the y-axis? Say these are all a1, a2, a3. Okay, so consider this is 1. Okay, just assume that this plane is a unit cube. So for a unit cube, what happens? All the sides are of length 1. So where does it intersect on the y-axis? It intersects at 1. Does it intersect anywhere on the z-axis? Does this plane intersect? No, this is running parallel to z-axis up, so it does not intersect anywhere on the z-axis. So the answer I can rate it as infinity. Okay, so once the intersection points are found out, the idea is take the reciprocal. What is the reciprocal of infinity? 1 by infinity. The reciprocal of 1 is 1 by 1, and the reciprocal of this is 1 by infinity. And this is your Miller indices. Take the reciprocal, that is 0, 1, 0. So the Miller indices for this plane is 0, 1, 0. Agreed? So let us calculate the Miller indices for this plane. Consider again, this is your x, this part is your y, and the upward part is your z. Now can you tell me where is this plane intersecting? You can see the Miller indices in this case is 1, 1, 0. Agreed? Now take this as a task, and I'll explain in the next lecture how this happens. So you can take this as a task too. Before solving this too, I'll give you some more hints about calculating Miller indices by using other examples. Okay, let us see some other examples. So consider this plane. Okay, check out that this plane is intersecting at 3 points here, okay, here and here. These are the 3 points, so it is intersecting. Say this point is 3a1. So a1 is the basic lattice vector, and the plane has this side as 3a1, and say this side it has 2a2. So it is intersecting here at 2a2, and up it is intersecting at say 2a3. Agreed? So what are the 3 points? The 3 points are 3a1. a1 is the lattice vector, 2a2, okay, and 2a3. So what is the idea behind Miller indices? Take the coefficients, reciprocal it. So this will be 1 by 3, this will be 1 by 2, and this will be 1 by 2. Now, after taking reciprocal, form the 3 smallest integer having the same ratio. Okay, what are the 3 smallest integer? That will be 2, 2, and 3. There will 2, 2. Oh, so yeah, so let me write it as 3a3. Okay, that will be better. So the smallest integer will be 2, 3, 3. So this is the Miller indices. So in case of 1 by infinity, you can write things as 0. In case of 1 by 1, you can write 1. But in this type of cases, you need to find the smallest integer. Okay, so let me give you one more case of Miller indices. Another example. Okay, I'm not drawing the diagram. So consider a plane. Okay, there is a certain plane, and the plane intercept at the 3 axis, and say the point of interception are 4, 1 and 2. Now if you are asked to find the Miller indices, what you'll do? Take the reciprocal, 1 by 4, 1 by 1, 1 by 2. Okay, now these are the reciprocals. So what are the smallest 3 integers? Well, can you frame the smallest 3 integers using having the same ratio? So the smallest 3 integers having the same ratio are 1, 4 and 2. So this is the Miller indices of this. So if the intercept is given, find the smallest smallest integer. Here also intercept was given, and you found the smallest integer having the same ratio. Okay, some more examples. So the more examples you do, then you'll get a clear idea. So consider this example where I have a plane here. Okay, I'm drawing a plane somewhere around here, and this plane, say consider 3 axes. So this is one axis, this is another axis, and this is the third axis. Now say this is x, this is z, and this is y. Okay, now say on the y-intercept the value, okay, so on the y-intercept the value is say 0.5. okay, now if you are asked to find the Miller indices, now we are actually finding the Miller indices of this plane. Now can you tell me, is this plane intersecting anywhere on the x-axis? No, so I write infinity. Where is it intersecting on the y-axis? It is intersecting at 0.5. 0.5 is actually 1 by 2 already. Now where it is intersecting on the z-axis? Infinity. So what the Miller indices says, take the reciprocal, so 1 by 0.5 and 1 by infinity. So what do you get? You get 0, you get 2, you get 0. So these 3 numbers are the Miller indices. Remember, Miller indices are represented by 3 numbers h, k, l, n. H, K, and L. So these are the Miller indices. So in this case, the Miller indices 0, 2, 0. Yeah, I will look at further examples to get a clear idea of what Miller indices is actually doing. So this example. So you see, I want to find the Miller indices of this particular plane. Okay, can you tell me where the plane has intercepted? The plane has intercepted on only Z and Y, but not on X, because it is running parallel to X. So I can write as interception happened at, say, this is unit cube. So this is a cube with A equals to 1. Agreed. Now what you need to do is, in X you need to put infinity because it is not intercepting. In Y it is 1. In Z it is 1. Now take the reciprocal. So it's 1 by infinity, 1 by 1, and 1 by 1. So what are the three Miller indices? You get 0, you get 1, you get 1. Okay, so these are the Miller indices of this plane. So we are, till now we are considering only 0 and 1. I mean, we are considering only unit cells, unit primitive cells. Agreed. Now let us look at some of the application of Miller indices. We'll look at only one application of Miller indices in special. Okay, an interesting theorem says, if you have a cubic lattice, okay, so if you have a plane of cubic lattice, if you have a cubic lattice and say you have a plane, you have a family of planes. Okay, for example, consider this is a plane, and you know the Miller indices of this plane as H, K, L. So these are the Miller indices. Now say this plane is part of a cubic lattice. Okay, somewhere on the cubic lattice. So consider family of plane. So consider another plane above this, the same plane, and the distance between these two planes is D. So when I'm saying family of planes, I mean many more planes. So consider the third plane, and the distance between the second plane and the third plane is D. Agreed. So if we continue in this manner, so there are a family of planes, and the distance between adjacent planes is D. Then there is a particular formula that relates this space between the planes and this Miller indices. The formula says that given the Miller indices of a plane, you can calculate the separation D, which is equivalent to A is the lattice vector divided by root over of the square of the Miller indices, that is H square plus K square plus L square. Okay, so this is an interesting application of Miller indices, that once the Miller indices of a particular plane is defined, you can actually calculate the spacing between the family of planes. So till now what we have done, a quick review. We learned about various types of various type of lattices. Okay, orthogonal, triclinic, cubic, rhombic, etc. Then we focused on cubic lattice. Under cubic lattice we had three types of lattice, that is simple, face centered, and body centered. In the three types of cubic lattices, we calculated packing fractions. I mean how tightly they are packed, that was given by the packing fraction value. And then we are studying about, suddenly we are studying about planes, and we are studying about the Miller indices. So this is what we have done. So all are haphazard. Okay, and these are something mathematical, and till now you are not able to see any interesting application, neither we are getting any interesting intuition behind definition of these things. But there are, when you study the reciprocal lattice, then everything will become clear. So in the next lecture we will actually study the reciprocal lattice in full detail.